All right, we're taking a look at trying to find the surface area of the portion of z equals square root 4 minus x squared that lies above the rectangular region where x ranges from 0 to 1 and y from 0 to 4. So if we do draw R, it's a pretty simple region. We're just going to go from, x goes from 0 to 1 and then y goes all the way up to 4. And we've just got a nice rectangular region. So really those are my bounds. We don't need to do anything extra or different. We can do x and y in either order. So from 0 to 1, or sorry, y goes from 0 to 4, and then x goes from 0 to 1. And this would also cue us in that we're likely going to keep rectangular coordinates because trying to represent this rectangular region and any other type of coordinates would be more challenging to do. So let's then try and set up our integral. So taking a look at what we're going to need, right, we're going to need z sub x. Taking a look at z sub x, we'll notice that we've got an x term underneath a square root. So that's really that whole quantity raised to the 1/2. So we're going to bring down that 1/2 power. Keep the inside, so 4 minus x squared. Decrease that power by 1, so that's going to go to a negative 1/2. And then chain rule, we need to multiply by the derivative of the inside, which the 4 with respect to x goes to 0, and then the negative x squared will go to negative 2x. So kind of simplifying that, if we put things where they go, we can see that then we've got negative 2 and a 1/2 are really going to leave just a negative 1. So we'll have a negative, and there's an x up top. And then on the bottom, that negative 1/2 power moves this square root 4 minus x squared to the denominator. All right. So then why don't we just do it now, because it'll be a little easier than trying to do it inside the integral. Then if we're squaring that, notice we're going to have negative x squared will just be positive x squared. That negative will cancel out. And then the square root is just going to cancel out because the square root times itself will be the quantity underneath. So we're really going to end up with x squared over 4 minus x squared. All right, we also in our surface area formula are going to need z sub y. Notice though, when we take a look at z, there are no y terms. So in terms of y, this entire function is a constant. So z sub y is just 0. So when we take a look now at our surface area integral, we're going to have that surface area is that double integral over the region R, where we do the square root of 1 plus z sub x squared plus z sub y squared. That was why we found those partial derivatives over there. And then we're doing this with respect to area. So plugging in what we found then, we've got the integral from 0 to 1, integral from 0 to 4. We would have 1 plus x squared over 4 minus x squared, and that's all under a square root. And then we're doing this, I put the integral bounds in the order of dy dx. All right. So at this point then, our goal is to try and simplify this integral here. So let's take a look at trying to combine the inside of that integral so that it's all not two different pieces, but rather just a single fraction. So we can take a look at having the integral 0 to 1, 0 to 4. If we get common denominators, right, we're going to have 4 minus x squared over 4 minus x squared for the 1 portion. And then we're adding x squared over 4 minus x squared. So then if we take a look at that numerator, we're going to have 4 minus x squared plus x squared. So those x squareds are going to cancel out, and we'll be just left with 4 over 4 minus x squared. And this is all in a square root, which if you think about at least the numerator of that square root, we can simplify. So we would have integral 0 to 1, 0 to 4. We really just have 2 over the square root of 4 minus x squared. And we have this dy dx. Okay, now that integrand on the inside is a little complicated looking, but notice the first integral we're doing is dy. And that entire expression in terms of y is just a constant. So we're going to have really the integral from 0 to 1. We'll have 2 over the square root of 4 minus x squared all times y. And we're going to evaluate that from 0 to 4. So taking a look, we're then going to see, we're just going to evaluate those into the y. So when I plug in 4, well, we'll get 4. So then I'll really have 2 times 4 is 8 over the square root of 4 minus x squared. And then when I plug in 0, it is 0, so we just have a minus 0. So then all of this is still just dx. So now we're left with a single integral. So we've got 0 to 1, and then 8 over the square root of 4 minus x squared. So when we start to take a look at this and think about what to do, a good idea first is to try and think, would a u substitution work? Right, because I have a function where I've got a square root in the bottom that's got a function of x inside, but if I do that u substitution, then I need that du is negative 2x dx. And I don't have an x dx in the top. So this normal u substitution is not going to work in this instance. So this is where we had to learn some other techniques. So this is going back to Calc 2. And one of the things we're going to try and remember from Calc 2 is when we had these situations where we had a square under a square root, our goal was to try and do a special type of substitution that had that square root cancel out. And this is where we used trig substitution. So u substitution didn't work, but we're going to try and do trig substitution. So my goal is to get this 4 minus x squared to turn into something that's equivalent to a perfect square. So when we think about our trig identities, I need to think about, well, which one is like a constant minus a trig function squared equaling another trig function squared. So if we think about it, well, my classic trig identity that we deal with is sine squared theta plus cosine squared theta equals 1. And if we think about it, we could subtract that sine over, so then we're left with cosine squared theta equals 1 minus sine squared theta. Now this right-hand side almost has the structure I want, except that it's a 1 minus instead of a 4 minus. So let's just multiply 4 everywhere. So 4 cosine squared theta is 4 minus 4 sine squared theta. Or another way to write that right-hand side is 4 minus 2 sine theta quantity squared. So what we can hopefully recognize now is what we're going to do is that trig substitution. So remember, with a trig substitution, we're replacing x with a trig identity, or with a trig expression, excuse me. So in this one, what we're going to pick is this expression right here. We're going to let x be 2 sine theta. Because what's going to happen then in my integral, let's just start to work over here for a second. I'll take care of the bounds in a minute. But in the denominator, at least, I'm going to end up with 4 minus 2 sine theta quantity squared, which we can see shows up right over here. And it's going to simplify down to a perfect square. It's going to become 4 cosine squared theta, which then is exactly what we're looking for, which will cancel out that square root. So let's take a look here. Sorry about that. I was adjusting my pen. Let's take a look here then at what else we need to do with a trig substitution, because we have other things that we need to sub in. Where notice we need to go from a dx to a d theta. So let's take this equation and figure out, well, what does dx become? What's it equivalent to? So if x is 2 sine theta, well then dx, taking that derivative, we're going to end up with 2 cosine theta d theta. And then we can probably notice the other thing that I still need to sub in is we still need our bounds. Now the bounds get a little bit interesting where we have to try and figure out a little solving, if you will. We could also, if we want to, you could leave the bounds in terms of x, and then later you could convert back into x's in order to evaluate. But let's see if we can just find our bounds so that we can just stay in terms of theta for the rest of the problem. So let's look at our lower bound first. Well, x was 0. So really what this means then is that 0 equals 2 sine theta. So really what we're looking for then is a theta that makes sine of theta equal to 0. And we're going to try and pick an appropriate value for that. Well, the smallest positive, well, non-negative value would be theta equals 0. Taking a look at our upper bound, we've got that we want x to be 1. Well, that's going to look like 1 equals 2 sine theta, or sine theta equals a half. And if I try and think about my smallest non-negative solution to that, we're going to think about, well, then theta, if we think about our reference triangles or our reference circle, we're looking for sine theta to be a half, which means we need it to be the lower of the two angles. It should be shorter than it is tall. So that's going to be theta is pi over 6. You could also make your reference triangle of your pi over 6, pi over 3, 90 reference triangle. So this is the one where you took an equilateral triangle and cut it in half. So we would have side length 2, 1, and then we can solve for the other one what it would need to be, which is square root 3. Because 1 squared plus square root 3 squared would be equal to 2 squared. That would equal 4. So then sine is opposite over hypotenuse. Sine is 1/2. So my new bounds are going to be 0 to pi over 6. And then we've got 8 times 2 cosine theta d theta. Because remember, the dx, we have to sub in an actual expression for it. So over here, then, we really have the integral 0 to pi over 6. We've got 16 cosine theta all over the square root of, remember, 4 minus 4 sine squared theta is 4 cosine squared theta. This was the whole purpose, the whole motivation for how we picked our trig substitution. So then we've got the integral 0 to pi over 6. We've got 16 cosine theta all over 2 cosine theta when you cancel that square root out. And now we can see this is going to be pretty golden for the rest of our problem. What we're going to end up with here is we're just going to have the integral from 0 to pi over 6. Notice those cosine thetas cancel out, so then we're really just left with 8 on the inside. 16 over 2 is 8. So a super nice integral now. So then we're just going to have the integral 0 to, actually, we can just do the integration. So we can just have 8 theta and evaluate that from 0 to pi over 6. So when we plug in pi over 6, we're going to end up with 8 pi over 6. And then we'll really just subtract off 0 because 8 times 0 is 0. So just dividing out a 2, we get 4 pi over 3 as our final answer.